Good afternoon, everyone. Thank you for joining us today for the 9th iteration of our Tech Talks webinar series. If you missed our previous webinars, you can find the recordings for those on our YouTube channel. Before we get rolling, I have a few housekeeping items to highlight. Please keep your microphone muted and your video turned off for the duration of the webinar. I greatly appreciate your help with this. This webinar is being recorded and will be made available later today on our YouTube channel. If you would like to submit a question for our speaker to answer, please make sure to send a private message to our moderator via the chat. And lastly, if you are having any technical difficulties, please use the chat to send a private message to our tech support team. Without further ado, we will introduce our moderator for today, Dr. Eric Rowe. Dr. Rowe is the Assistant Dean for Continuing Education at the Cockrell School of Engineering, as well as the Executive Director of Texas Engineering Executive Education, which is the continuing and professional education provider of the Cockrell School of Engineering. Take it away, Dr. Rowe.
Thanks, Javier. Welcome to our webinar. In these Tech Talks, we look to share exciting and industry-relevant topics happening here at UT and the Cockrell School of Engineering. If this is the first time you're joining a Tech Talk, the format is the following. I'll introduce our speaker. He'll present for about 30 minutes. As Javier mentioned, as you think of them, please type your questions in the chat window. And at the end of the Tech Talk, we'll leave some time to address your questions. An exciting topic today. Our speaker today is Dr. Peter Stone, one of the most widely cited researchers in reinforcement learning and robotics. Dr. Stone is the David Breton Jr. Centennial Professor and Associate Chair of Computer Science, as well as the Director of Texas Robotics at the University of Texas at Austin. He's a UT Austin University Distinguished Teaching Professor. Professor Stone received his PhD in computer science in 1998 from Carnegie Mellon University. His research interests in artificial intelligence include machine learning, especially reinforcement learning, multi-agent systems, and robotics. From 1999 to 2002, he was a senior technical staff member in the Artificial Intelligence Principles Research Department at AT&T Labs Research. He is an Alfred P. Sloan Research Fellow, a Guggenheim Fellow, an AAAI Fellow, an IEEE Fellow, an AAAS Fellow, a Fulbright Scholar, and 2004 ONR Young Investigator. In 2007, he received the prestigious IJCAI Computers and Thought Award, given biannually to the top AI researcher under the age of 35. In 2016, he was awarded the ACM SGIA Autonomous Agents Research Award. Professor Stone co-founded Cognitai, Inc., a startup company focused on continual learning in 2015. He currently serves as Executive Director of Sony AI America. Peter, thank you for joining us, and thank you so much for sharing your work at today's Tech Talk. Handing off to you.
Thank you very much. Thanks for the very kind introduction, and thanks to all of you for being here. I'm going to try. I've been told that this is an audience that's a technical audience and sort of interested in some of the details, but also not exactly in the research area of mine necessarily. So I'm going to try to sort of give both an overview of my research and also some of the technical details about the field of reinforcement learning in general, and then sort of one small technical sort of dive into one area of current research that I'm working on. So there'll be sort of a mix of high-level overview and a little bit of a deep dive. So and I'll try to leave plenty of time for questions at the end. So one goal of artificial intelligence and robotics, it's not the only goal, but one that I've have always subscribed to, is trying to create robust, fully autonomous agents in the real world. So what do we mean by fully autonomous agents? I mean, agents, so an agent could be a robot, it could be a computer program of some other kind, but it's something that senses its environment, has some decision-making to decide what actions to take based on those sensations, executes the actions, and then those executed actions affect its next sensations. And so a question is, how would how would one go about doing this? At the beginning of the field of AI, which is really only, it's a young field, around 70 years ago, there was only one way to proceed, which was to sort of decompose the problem into various subparts, and to work on maybe some people working on computer vision, some people working on the decision making, some on the action, some on natural language, and then hope that we can get those pieces to come together. But in the last couple of decades, we've been able to sort of take advantage of some of that early progress, and instead go from the other direction, trying to build complete agents to perform increasingly complex tasks. And by a complete agent, like I say, I mean something, a program or a robot that can sense, decide, and act in a closed loop. By a closed loop, I mean there's no human intervention, that it can just keep sensing, deciding, acting, and continuing on over time. And the idea is that if we can build these complete agents, that this will drive research on component algorithms and theory. And the particular areas that my research focuses, and that I'll touch on today, are machine learning, because an autonomous agent, if we're going to consider it to be robust in the real world, it's going to have to be able to improve from experience. If you have an autonomous car, it backs out of your driveway and drives through the same pothole every single day, you're not going to be considering it very intelligent. You want it to learn from experience how to avoid that. And then the other main area of my research is multi-agent systems. Again, using the autonomous car as an example, if you have one, you're not going to be the only one with an autonomous car. That car is going to have to interact with others on roadways. Your neighbors will have them, and so this is the field of multi-agent systems. So I've been working in artificial intelligence for the last quarter century or so. I recently got to that point where I can say that. It makes me feel a little old, but back when I started in the early to mid 1990s, it was not, there was not much hoopla around the field. In fact, people had thought of it as sort of an area whose time had come and gone. It was what we sometimes call an AI winter. But since then, as you know, we're now at sort of a peak in what I like to call the hype cycle of artificial intelligence. It's a little bit, everybody is a lot of people are very optimistic about the possibilities. This has happened before in the history of the field, and so I think we'll probably see continued cycles. But throughout my time doing research in this area, this question, the one I have on this slide, is the one that's driven me, and it's the one that really is providing a career's worth of research inspiration. It's to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? And so in my research lab, we both do research from the theoretical, starting from the theoretical components and basic algorithms that are general purpose, which I call sort of bottom up, and then also more top down application oriented research. And so as a one slide introduction to my lab, it's a lot easier to talk about the latter, to tell you some of the application domains that have inspired the research and show you some examples with some videos. But first, just to narrow the focus, I do research in artificial intelligence. There's some sub areas of artificial intelligence that our research is most relevant to: autonomous agents, multi-agent systems, and then in this talk, I'll especially emphasize robotics and machine learning, especially reinforcement learning. So like I say, there's some application domains that have driven my research. One is robot soccer. So this is a video of some old Sony Aibo robots from about 15 years ago playing in a robot soccer competition. You saw one score a goal there, where they're completely working autonomously. There's nobody remote controlling those robots. They need to sense the ball, decide what action to take, execute that action. We now are a part of the, we've now moved on from those Aibo robots that look like dogs to these humanoid robots. So this is a clip from the 2012 finals of the robot soccer competition. Our team playing against a team from the University of Bremen. Our team is the one with its hands behind its backs, which we did to sort of help with balance and to not run into other robots. Here you see our robot going in on a breakaway. And again, you have to remember that the robots are like fully autonomous. We program them, but then once the game starts, we just have to see how their actions, their sensing, their perception of the ball and where they are in the field, their actions of walking and kicking, and their decision making all work. And here you see a goal being scored. The robot calmly banks it off of the goalpost. We went on to win that game 4-2. We became the RoboCup champions for that year, the Robot Soccer World Cup. And when we came back to campus, they lit the tower orange for us, which we were very, very happy about. I'll talk a little bit more about RoboCup and robot soccer as a research inspiration as I go, but just to some other application domains I've been interested in. If you come to my lab in the computer science building at UT Austin, and now in the new robotics facility, which is in the old Anna Hiss gym, you'll often see robots like this one just wandering around the halls. You don't need to ask us for a demonstration. We just try to have these robots always on and become a part of the social fabric of the building. We call it the Building-Wide Intelligence Project. So in this particular video, we're showing the robot in some joint research with my colleague Ray Mooney. The robot's learning to improve its understanding of natural language processing by having people type in dialogue to the robot, and if the robot doesn't understand, it asks questions, and so it learns more and more about the meaning of different words and the intentions of people. But this is just one example of the general challenge of service robots, which again I'll talk about a little bit later, but of having robots interacting with people in an always-on, long-term autonomy kind of mode. And then finally, I have been involved in with autonomous cars as well. I had a car in the DARPA Urban Challenge in 2007. So this one sort of here in the back is our car that we went to the finals of the DARPA Urban Challenge in 2007 with a bunch of undergrads from a research class I was teaching. In this case, the car has no person inside of it. It had to do sort of find gaps in traffic and turn so that it can merge in with traffic, and it did 8 loops in about 20 minutes. We've actually since retired that car. As you know, many of the autonomous or many of the car companies in the world are building their own autonomous cars, and some other companies as well. And so our sort of one-off prototype wasn't particularly sort of sustainable, but we still think a lot about what the world will look like when all the cars on the road are autonomous. Will we still need traffic signals and stop signs, or will the intersections look a little more like this? And this is what I think that intersections could look like with autonomous cars. What's going on here is the cars that are white have already called ahead for a reservation with a computer agent that's that's sort of in place of a traffic signal. And if they're white, they already have a reservation. If they're yellow, they don't, so they have to stop. But once they turn white, they have a guaranteed path through the intersection that won't intersect with any of the other cars. Just as a side note, one of the first time I showed this video, again, almost 15 years ago, it was at a conference in India, and people said, well, that's what all the intersections look like. But the difference here is that as long as the cars are following the protocol, we can guarantee that there won't be any accidents. And this is in a case where all the cars were autonomous. We've since done a lot of research on what happens if you have a mixture of human-driven cars, autonomous cars. What if you scale up to multiple intersections? There's lots of, I could give sort of an hour-long talk on any of these. But the purpose of this slide is just to sort of give you some insight into to the challenge problems that motivate my research in artificial intelligence. So to continue on with in this talk, it's sort of going to be in 2 parts. There's going to be a little bit more motivation, and in particular, I'll talk some more about the Robot Soccer World Cup and RoboCup, and I'll give a really brief high-level introduction to reinforcement learning. Some of you may already be familiar with it. Those of you who are not, it's sort of one of the buzzwords in artificial intelligence these days. And so I'll try to give just sort of a high-level view of how that works. It's a core part of the research in my lab. And then, like I said, I'll give sort of a technical deep dive into one particular problem, which is we call the sim to real problem, which is how do you learn behaviors in a simulator and try to get them to work on real robots in the real world. And I'll introduce a method that I call grounded simulation learning for that. So first, RoboCup Soccer. I'm actually right now serving as president of the International Robot Soccer Federation, which is a group of thousands of people around the world who share a common, very ambitious goal. It's good to have ambitions. The goal is by the year 2050 to be able to create a team of humanoid robots that can beat the best human soccer team on a real soccer field, an outdoor soccer field. So, this is who knows if we'll be able to do this, but this is sort of in the spirit of trying to beat the world chess champion that Deep Blue did, and the world Go champion that AlphaGo did, and the world Jeopardy champion that Watson did. And but this is taking it to the next level because there's a physical aspect to it, actually having real robots that can move around in the real world. And we've been working on it for years, but there's still more than around 30 years to go. The reason we picked 2050 is we learned long ago, if you're going to make a prediction in artificial intelligence, make the date after you're likely to have retired, so nobody holds you to it. There's a lot of unpredictability, but we've made a lot of progress. There's a lot of first of all, as a challenge problem, as an inspiration for research, it's got a lot of great features. It does allow us to build closed loop systems that can sense, decide, and act, even if it's not on a real soccer field with human-sized robots, with sort of on a smaller field, maybe with a smaller ball, or with fewer robots. And we've been able to do that since 1997. We can get multiple robots working together, and it's possible for people to enter this challenge from lots of different backgrounds. There's different leagues, soccer leagues within RoboCup. I'll show some videos of some of them. In fact, in the 1997 and 98 years, like I say, we already had multiple robots working. It's sort of embarrassing to watch these videos now. These are not all my own robots. These are robots with colleagues around the world, because the robots are falling over, they're running into walls. You don't see it on the videos. Sometimes they even caught on fire. But they actually worked. They sensed, decided, and acted. There were some goals scored. As you see here, there wasn't much goalie opposition there. When they fell over, they did get up. There were robots working, and each of these videos is sort of from one of the different leagues. The commonality among all the leagues is that the robots in all cases are fully autonomous. If you jump ahead to several years, you now see that the robots are much more individually capable. They're faster, they're shooting harder, they're passing, and you can see very, very noticeable improvements. Down in the bottom right corner, you see the beginnings of the humanoid league, so they just had a penalty shot competition that year. But now, if you watch, you can find videos of seeing the humanoid robots playing in real games as well. I showed you one of the standard platform league earlier, which is the one where everybody has the same robots. One of the competitions that my team has focused on, I have a team called UT Austin Villa, and we've dominated in this 3D simulation league, which is shown here, where there's it looks sort of like a video game, except unlike a video game, the robots are all controlled independently. And it's in a physics simulation environment, so it's hard to just get them to stand up without falling over, to kick. We use a novel machine learning method, a hierarchical machine learning method called layered learning. This highlight here is my student's favorite highlight. He always makes sure that I show this one, where I hadn't planned it, but the robot manages to kick the ball through the leg of the opponent into the goal. But this is, it's a great challenge for both learning of individual skills and also the teamwork aspects, trying to get the robots to work together. Oops, that's not the one I want to show. Finally, I did mention that our goal is to be able to beat humans. We do have play games every year. The winner of the middle-sized league that uses a real soccer ball, we play against myself and some of the fellow trustees of the RoboCup Federation. So far, we're still able to sort of run circles around the robots a little bit, and we can beat them without too much trouble, even though we're aging amateur soccer players. But every year it gets a little bit more difficult. And some people say that's just because we're getting older, but it's also actually quite noticeable that the robots are getting better. In addition to RoboCup Soccer, there's also RoboCup actually isn't just about soccer. It is also about service robots as well. And there's also RoboCup Rescue. There's a RoboCup Junior. The service robots are in an area called RoboCup at Home, and this is in a collaboration with colleagues here at UT Austin and in some of the engineering departments, in particular Luis Sentis in aerospace engineering. We have this Toyota HSR robot trying to do sort of what we call service tasks. So here's one where we have it programmed to take out the trash. and this is one of the events in the RoboCup at Home competition. And the robot also has to do other things, like there's groceries on a table. It needs to put them away on a shelf where the similar items have to be placed near each other, but nobody tells the robot ahead of time what it means for an item to be similar. So it has to sort of have some comprehension of what the different items are used for. There's human robot interaction where it needs to take requests from people in the environment, and various challenges of autonomous robotics. And so here the robot is just trying to deposit the trash in sort of in a takeout zone and then go find the other trash cans in the environment. But it does also, in one of the tasks, the robot has to go and serve drinks or different items in a restaurant that it's never been in before. It needs to find a customer that's waving to it, go over to it, hear it in natural language, trying to ask for the Pringles or the Coke or the Sprite. The robot has to go find the appropriate item and bring it to the person and actually pick it up and manipulate it. So these are the kinds of challenges we're working on. And the one thing I want you to appreciate is that these are not at all the kinds of tasks that you can solve by just throwing a deep neural network at it. And this is sort of what a lot of the uptick in excitement about artificial intelligence recently has been the power of neural networks and deep learning. And they're great at some things, but there's still many tasks that are far beyond the capabilities of a deep neural network with the amount of training data that's feasible to give them. And these are the kinds of tasks that inspire a lot of this research, where we still need to merge some of the traditional artificial intelligence methods, including probabilistic reasoning and planning and logical reasoning with neural networks. So that's by way of sort of giving you a sense of the problems that are inspiring to me in my lab. I said I would give sort of a little bit of an introduction to one of the current buzzwords in artificial intelligence, one of the research areas where we've contributed to the most, and it's an area called reinforcement learning. And again, apologies for those of you who already know how reinforcement learning works, but from a high level, it's in contrast to most machine learning methods that people know about these days, which we typically characterize as supervised learning problems. And supervised learning problems are those where you have a bunch of training examples, like shown on the left here, with their correct labels. So these are handwritten digits and the correct, this is a 4, this is a 3, a 1. There'll be, and if you give a computer, millions of these kinds of examples, then eventually, if it gets given a new digit like this one here, it'll be able to label it as an 8. And that's what deep learning is best at, given large training, labeled training sets, having them learn to predict what the label of a new element would be. And so this, you can do much more sophisticated things than this in language translation and image recognition and things like that. But for autonomous agents, these robots or things that need to sense, decide, and act, there's another paradigm, sort of another class of learning problems that's more appropriate, and that's the reinforcement learning paradigm. So again, it's a different type of problem. It's not a different algorithm for the same problem, but it's a different class of problems. And it's the problems where you're trying to for a new agent, learn a policy, where we characterize a policy pi as being a mapping from states to actions. So, if you're a chess playing agent, then the state would be where all the pieces are on the board, and the action would be what move do you want to take. If you're an autonomous car, the state would be where you are in the road and all the other cars around you, and the action would be what should you do with the accelerator or the steering wheel. And the key aspect here is that you execute that action in the environment, and then you'll get a new state back from the environment and possibly a reward signal as well. And crucially, the right thing to do doesn't depend on the immediate reward signal, but instead a delayed reward signal. So when you're playing the game of chess, you make a move and you don't know whether that was a good move or not. You have to make a lot of different moves until you find out whether you won or lost the game. And then it's up to the agent to go back and figure out what were the good moves and what were the bad moves. And so this kind of problem can be formalized as what we call a Markov decision process. This is a very small schematic of a Markov decision process where the states are in green and the actions are in red. So for instance, from state 2, there's 2 possible actions. You can take action A0 or A1. So that's what you have to decide in your policy. And then after you do, there's probabilistic transitions. If you take A0, you with 0.4 probability, you'll move to S0. With a 0.6 probability, you'll stay in the same state. And then occasionally when you take a transition, there's a reward that's emitted. Like, here, a +5, here a -1. And the key is you want to try to find the actions that lead to the highest reward in the long term. So you might want to take an action that gives you that -1 if it takes you to a state that will, from which you can get a high reward in the future. And there were some really beautiful foundational theoretical results on reinforcement learning in the late 1980s and early 1990s. But it's only recently that there have been sort of scaling up to more complex applications that has come from the ability to have a lot of computation and get a lot of experience in certain domains. So the theoretical result that was really invigorated the field was a particular algorithm called Q-learning that we can, and I won't tell you the full details of it, but just the way it works is that it learns what we call a value function, which is illustrated here. A value function is a mapping from state and action. So again, you could think of that as a chessboard and move your pawn or move your knight on these 2 different axes to a value, which is shown by the height of these bars, which says, if I were to take this action from that state, what's the expected reward I'll get if I act optimally in the future, take every action afterwards in the future optimally. And if you can learn that value function, it's trivial to decide what to do. Just in a state, you look at your actions and decide which has the highest bar here, which has the highest value, and you select that one. So the key is learning this value function. And it turns out that with a very simple update rule from experience based on your current state, your previous action, and the immediate reward, you can do a sort of a gradient descent kind of update that will eventually converge to the optimal value function, the true value, and then allow you to find the optimal policy. It's a very elegant algorithm in some ways, but it's also a very simple and inefficient algorithm in other ways. It requires visiting every state infinitely often, which clearly doesn't work if you have a huge state space. So in practice, it's important to be able to generalize, to be able to learn from some states what will happen in nearby states. And so this is where what's now called deep reinforcement learning comes into play. People often use a neural network, but you could use any function approximator to generalize across this state action space. In this case, the theoretical guarantees are harder to come by, but there's been a lot of great empirical successes, starting actually from the mid-1990s, where there was a world champion backgammon player learned with Q-learning. In the early 2000s, there was some helicopter control. And then some, a little over 10 years ago, some medical applications and some sustainability applications. And most famously, in the much more recent times, Google's DeepMind beat the human Go champion using essentially this deep reinforcement learning algorithm, this Q-learning algorithm with a neural network function approximator embedded. So that's sort of an overview of reinforcement learning and some of the motivation for my research. I'm going to use the time that I have left to give you a sort of a little bit more of insight into some of the ongoing research that's going on in my lab, and in particular on this method called grounded simulation learning. And this is joint research with two former PhD students actually now. So Patrick McAlpine went on to Microsoft Research and is actually now at Sony AI with me. Josiah Hanna graduated just last year and is about to be faculty at the University of Wisconsin-Madison after doing a postdoc at University of Edinburgh. And the idea is we want to try to take this methodology that was used on for Go to great effect by Google, and try to get it to work on real robots. Now, what's the problem with that? To learn in Go, you had to play millions of games of Go. And with real robots, it's hard to do anything a million times, let alone even 100 times. And so to learn on these physical robots, we need to be much more data efficient. And we'd ideally like to be able to, not have to, supervise the robots and have them fall over while they're learning and do all of, and have all of these things happen. So that's what motivates learning in simulation. It would be great to just say, well, let's build a simulator of the real world, try to execute lots of thousands of trials in parallel, and we don't have to supervise the robots, and just they can reset automatically. And then, so we can then set up like a training paradigm like this, where our robot is learning how to dribble a soccer ball, but you could also just have it try to learn to walk fast by running overnight, and then we come back in the morning and see how it's done. And the problem with this is that of course, it all depends on how good your simulator is, and no simulator is perfect. And this is it's a lesson we've learned over and over again in the field, is that no matter how much effort you put into building a good simulator, it's never identical. And so you can take a policy that's learned in simulation like this one, and it'll execute on the real robot, but after a few steps, it just falls over. And this is because of the differences between the simulator and the real world. So in just to dive into this and to formalize this a little bit, you can think of there being a real environment and a simulated environment that are the same in the sense of they take the same kinds of actions as input, and they give the same kinds of states and rewards as output. But the main difference is, and therefore you can execute the same policies in both environments, but they have different dynamics. In other words, if you take the same action in the simulated environment that you took in the real environment, you'll get a different transition, a different next state in the that results. And so there's a number of different ways to try to address this. There's a class of algorithms that tries to learn a robust policy by injecting a lot of noise into the simulated environment, and then hoping that the policy that you learn will be robust to this noise, and that noise will be reflective of the difference between the simulator and the real world. And so there's been some good success with that kind of approach. The other class of methods, and the one that I'm going to focus on today, is one where you take a small amount of data from the real world and try to use that data to improve the simulator over time. Now, most people who do this have tried to use it to build a perfect simulator. The premise of our research is that that's impossible, that you're never going to get a perfect simulator, but rather you can get a simulator that's better than the previous one you were working at in the part of search space where you're currently searching. So we introduced an iterative learning method called grounded simulation learning. That works as follows. It takes a real world execution of the policy for a small number of cycles, and then goes through a simulator grounding step, which I'll describe on the next slide. In that grounded simulator, then tries to improve the policy in simulation, and then takes that improved policy, executes it in the real world, and then continues through this loop, gets some new data, regrounds the simulator so that now it might get worse. It might become a worse simulator in some parts of the search space, but it's going to be a better simulator in the part of the search space where you're currently searching. And so the way this works, you can imagine trying to just learn a simulator from scratch. We actually take the approach that the simulator is a black box, that we can't go in and change its parameters. Instead, and that makes this a more general method. There are simulators where you can go in and actually manipulate them, but instead we're going to learn a wrapper, something that transforms the actions of a policy before they get passed into the simulator, that can do the grounding that I'm talking about. And in particular, we learn a grounding function that I call G, that, as I say, replaces the real action that comes out of the policy with a substitute action that has the same, that's predicted to have the same effects as if the original action had been executed in the real world. And so we're going to use machine learning to learn this function as a function of the state and current action. To open up this function, we actually do this as a two-step process. We learn first a forwards dynamics model, which is a function that takes in your current state and your action and predicts what the resulting next state will be. And then we learn, and that's a forwards dynamics model of the real world. And then we learn an inverse dynamics model of the simulator, which is a function that says, if I was in state S and I want to get to state ST hat, what action do I need to execute to make that transition happen? If you learn both of these together, then you can compose these functions and get an action A that gets fed in. You figure out what resulting state the real world would give you, and then find the action you need to give to the simulator to get that same state. And so if we learn this function, we should get a simulated behavior that's very similar to the behavior in the real world. We do this by learning using a deep neural network, as is the fashion these days. So we train with some real world trajectories, and then the inverse model with some trajectories in the simulator, and then we can see how this works. We can learn from the simulator I've shown you before, or we have another simulator, and then we have the real world. We can there's 3 different kind of transfers here we can try. The results I'm going to show you, we started with the fastest known walk on this robot. It was created by some colleagues at the University of New South Wales. The policy search algorithm that we use in the simulator is called CMAES, which is a stochastic parallel policy gradient reinforcement learning method. I'm not going to go into the details of it, but basically, we can run for thousands of iterations in the simulator overnight to come up with a really good policy to learn in our simulator, and then we can try to execute that in the real world, and then repeat. And so, just to give you a sense of how this works, here's the starting policy, the one that was programmed by our colleagues in Australia at the University of New South Wales. It was the fastest known stable walk for this robot at the time from around the world, going a little less than 20 centimeters per second. We started from that point and used this methodology to improve our simulator, and then optimized overnight, and then execute the policy. And we ended up with already a policy that's 26.3 centimeters per second. And then we reground the simulator and repeat one more time, and we get to what was the fastest known stable walk on this robot at the time. And you see it's sort of a little more squat to the ground. It's going 28 centimeters per second. So just in summary on this, this is some ongoing research, the general area of grounded simulation learning for sim to real. We've actually done some follow-up research, which I could talk about more, but I think I want to leave more time for questions. The key here is that we've improved a state-of-the-art walk engine for this now robot by over 40%, and created the fastest known stable walk on the robot. There are a lot of extensions. We have been extending it to other robot tasks and platforms. We're understanding theoretically when does grounding actions work and when does it not. We're connecting to off-policy evaluation and safe learning, which are sort of more technical topics in reinforcement learning theory. And we have actually 2 papers that are extensions of this that are going to be presented at the IROS conference, one of the main robotics conferences just next week. So just to return then, to the research question, the general area that I'm interested in is autonomous agents, and especially focused on robotics and reinforcement learning. We've got a whole bunch of different testbed domains. I will, a bunch of other things I could talk about, but again, I'm gonna stop in just a second and invite questions. But just to step back a little bit, some of the other contributions we've made in reinforcement learning are learning from positive and negative feedback, and learning from demonstration. So where the agent doesn't have to just learn by itself. One of our successes is an algorithm called Tamer that learns to play the game of Tetris. You can actually, hear this is sort of before learning. A person is giving feedback, which you can see by this top left corner. It's flashing green when the person's saying good move, and red when the person's saying bad move. And you'll see that even from the beginning of learning, which was completely random, to just a few seconds in, it's starting to do reasonable things. And if we flash to just the third episode of learning after failing on a couple of games, it learns a policy that's quite competent. It's possible to learn this game without any human feedback using reinforcement learning, but it'll take hundreds of thousands of practice games. We've developed an algorithm that allows this human feedback to make the learning happen much more efficiently and much more quickly. And we've applied that on real robots. We also work a lot in transfer learning or curriculum learning, enabling artificial intelligent learners, agents, to do the kinds of things that people do. When if you teach a kid to play checkers, you might first teach them tic-tac-toe, then if you want to teach them chess, you might first teach them tic-tac-toe, then checkers, then chess. We're trying to get autonomous agents to be able to learn from different tasks in this way as well. I've looked at other applications like reinforcement learning for playlist recommendation and other robotics problems. And then just to give a little bit of an insight into some of the multi-agent systems work we do beyond the traffic management that I've already talked about. Very interested in this concept of ad hoc teamwork, which is creating autonomous agents, artificial intelligent agents that can cooperate with other agents that were not controlled by themselves. And again, this is that motivation of, if I have an autonomous car, there's going to be other autonomous cars on the road, and they're going to be controlled by other programs. People are very good at this kind of thing. I can go play a pickup soccer game with people from around the world who I've never seen before. I can't even speak their language, but we can, immediately get onto a soccer field and start kicking a ball and behaving reasonably. We'd like to bring that capability to robots. So if there's a disaster like an earthquake, and I bring a robot, and you bring a robot, and people from around the world bring robots, we don't want to have to reprogram them to become a team. We want them to be able to figure out on the fly how to work together, what role they should each play within this team, what their strengths and weaknesses are, and how to work together. So the challenge is to create a good team player. And I introduced this as a challenge problem to the AI community about 10 years ago, and there's been a lot of work in this area of ad hoc teamwork and multi-agent systems. And we have, we've played some actually pickup robot soccer games where there's teams of robots that are created by different universities. Each one gets to just put one robot down on the field. They haven't coordinated ahead of time, and they have to somehow form a team on the fly. So I think with that, I could talk about any of these topics at much more length. But in the interest of having time for discussion and for questions, let me stop here and be happy to answer any questions people have.
Great overview, and it sparks a lot of thought. So thank you. Hey, I remember the robot soccer win, and when the tower was illuminated orange, and that was great. A fun question: have the robots ever scored against the humans in the robot-human matches?
Yeah, they have, but usually that's because one of our members of the board of trustees is very always says, let's let the robots show what they can do. Let the people, so we always, we score a goal, and then we start walking and passing and giving them a little bit of a chance. So I think that, the sense is so far that it's a mismatch, but yes, there have been some goals. I think if you search online, you can find there's some actually particularly pretty ones. But I have to say we're not at full strength when they happen.
So Austin FC won't have anything to worry about for a little while.
Not yet, but I don't see it as anything to worry about. Maybe it's a recruiting opportunity eventually.
Great. So let me ask you one of the questions from our participants.
Sure.
Have you done any research, or are you aware of research linking the individual robot or computer agent activities to patterns observed for the entire group? And I think you touched on this. The example, energy consumption of the agents, their work output. And then related, do your autonomous robots, the ones in the engineering building there, do they access energy themselves, plug themselves in? What was the learning associated with that?
Yeah, so I mean, there are robots that can self-dock and sort of recharge by themselves. There's probably one of the best examples is the robots at Amazon Robotics, formerly Kiva Systems, that do automated warehouse. So they bring the shelves for people to pick things off of the shelves and put them in boxes when you order something from Amazon. Those robots were actually developed by an alumnus of the RoboCup competitions in the early years, Raf D'Andrea and some of his colleagues. And those robots do self-dock and self-charge. The IBOs were actually capable of that as well. The ones that are wandering around in our hallway right now, we haven't taken the time to give them the self-docking and self-charging capability, but it is something we're considering. And that would be more of an engineering, something we just need to engineer in. I don't think it's something we could have the robots learn to plug themselves in. They'd have to have the right manipulators or the right dock. But we do have them monitoring their power. So the robots do email us when their battery is running low and try to get themselves back to their sort of home base where the charging station is, so that a person can plug them in. You asked about the sort of emergence of the effect of a single agent on a group. One of the videos I didn't show in the ad hoc teamwork context, there's a PhD thesis from my former student Katie Genter. She graduated just a couple years ago, and she looked a lot at the problem of motivated by flocks of birds. If you imagine that each of these dots here on the screen is an individual bird flying towards flying toward an airport or something like that that's right beneath it, and each one changes its heading based on the headings of its local neighbors. The question that Katie asked was, what if we can insert a few agents, the ones shown in pink here, into the flock, such that they're under our control, but they're perceived by the other agents as if they were members of the flock. So that and there actually is evidence of this, that you can make a robot bird that other birds sort of interact with as if it's a real bird. And so in this video, we show that that we can control just a few of these pink agents can change their heading to be able to get the whole flock to change its direction. And so if there were an imaginary airport around here, you can sort of think of this as us steering the flock around the airport for the safety of both the birds and the airplanes. And so we've asked questions in this research about how many of these pink agents do we need? Where should they be placed? What should their control policy be? This is one of the kinds of questions that we ask in sort of the context of ad hoc teamwork or multi-agent systems. So I don't know if that's relevant to the question that was being asked, but that's something that I think is connected.
Yeah. So kind of aligned with the sim to real discussion, could you speak to the challenges when adopting transfer learning or domain adaptation methods from a general setup to an industrial setting? And for example, the ideal general setup, the source and target tags usually have the same input and output space, but that's not really practical in industrial setups, right? Where there's input sensor signals are likely different across different machines. The output labels are different. So how is this work being adapted in an industrial space?
Yeah, and there's a lot of different. So in industrial, I wouldn't make the characterization as being between academic versus industrial. I think there's lots of industrial settings where the assumptions that we're making do hold, and then there's other industrial settings where they're going to be different. But if the question is about what happens if the inputs and outputs do differ, I think there are a number of different ways to deal with that. So the first the first line of attack is always to create a learning scenario in your simulator that is broad enough and general enough to capture all of the scenarios you wanted to apply it to. So if you know what the variety of different machines or variety of different environments you're going to need to be robust to is, then you either you separate them out and learn separately for each setting, or you create the training environment to be general enough to be able to handle all of them. And so and this can be done. That's the sort of the first line of attack. But if there's sort of unknown, if you want to be robust to the sort of unpredictable kinds of effects, then that's where you need to sort of, inject noise also to the simulator, or try to do this iterative approach of regrounding the simulator to match the real world based on data. So I mean, I think there's, these kinds of methods do have promise in industrial settings, but of course, it depends. It depends on exactly the setting, and so I think it's hard to answer that question in one in one monolithic way without knowing the scenario that the person asking the question has in mind.
So going the other direction, I like this question. Do you have any takeaways from your research that tell us how or why humans act and learn as agents or collectively in ways that we may not have known without research such as yours into AI, ML, and robots? Yeah.
Yeah, that's a great question. And so, just to back up, I mean, I said one of the goals of researchers in artificial intelligence and robotics is to create robust autonomous agents. Another goal is to understand how the brain works. And some people, that's their motivator. And I think the confluence of multiple different fields, neuroscience and artificial intelligence and psychology, and to some extent philosophy, that has sort of become the area known as cognitive science, that tries to get at these kinds of questions. And yes, I've collaborated both with neuroscientists and with psychologists to try to understand what can we learn about human intelligence from this kind of research. So with a neuroscientist colleague of mine, Mike Mock, in the neuroscience department, he has one of the highest fidelity simulators of the mammalian cerebellum, the part of the brain that does sort of fine motor control. And these are the kinds of tasks that we can also do with reinforcement learning. So we've asked questions about, given the same input-output streams, to what extent does his cerebellum simulator learn in the same way or different ways from our reinforcement learning agents, and in what ways can those be brought together? So that's, those are sort of neuroscience connections. And then I've also collaborated with psychologists. So this video that I showed of learning in Tetris, it relies on a human giving feedback, but we asked some questions with them about how do people change the feedback they give as the agent is improving its performance. And there's evidence that at first, if a person in this kind of teacher role at first will just sort of give good positive feedback for anything that looks remotely successful, like you didn't stack the block in exactly the wrong place. And then as they see the agent learning, they'll stop giving positive feedback for that and start giving positive feedback only for actions that are relatively better than the current policy, and might start giving negative feedback for actions that they would have given positive feedback for previously. And so, recognizing how people interact with robots and then building our algorithms to take that into account is definitely something that we think about. We're also, in human robot interaction, one of the testbed domains we're looking at right now, I didn't talk about this at all in this talk, is having some of these service robots, the building-wide intelligence robots, try to figure out how to pass people in a hallway. And it turns out that when two people are walking towards each other, there's a lot of signaling that goes on, that people look in the direction they're going to go, but then they look away to say, I'm not paying attention to any change you might make. How can a robot engage in this kind of signaling with people? That's a part of human robot interaction studies. And so yeah, and then it does go hand in hand. How do we improve the robot algorithms, and how do we, through our experiments, learn the way people behave so that we can give that knowledge to the robots and have them more prepared to interact well with people? So yeah, it's a great question. It's one that I think, artificial intelligence really is in an ecosystem with psychology and neuroscience, in trying to understand just what is the nature of intelligence, be it natural or artificial.
Yeah, and one of the NAE grand challenges, right, to reverse engineer the brain. So certainly on a global scale, one of the things that we're very focused on in the STEM area. Mm-hmm. So kind of looping back, and I know we're running out of time, so I want to leave a couple minutes to close, but back to the soccer where we started. Have you been looking into, and are you using transfer learning in the robot soccer? And if so, what was your experiences? What came out of that?
Yeah, in fact, some of our we were some of the first one of the first research groups to explore the nature of transfer learning in reinforcement learning back in like 2004, 2005. And my former PhD student, Matt Taylor, who's now faculty at University of Alberta, wrote some of the seminal papers in this area. And we have a well-known survey of transfer learning for reinforcement learning. And the setting that we used as our test bed was a sort of a small scale robot soccer environment where we had robots learn to play 3 versus 2 keep away in the simulator. So just had, three. I might even be able to. Let me see if I can quickly show a demo of this. It might not work. Let's see if I can. No, it's not going to work right out of the box, so I won't try to fix it on the fly. But basically, we had a 3 versus 2 keep away scenario, which soccer players or soccer coaches will be familiar with, where 3 players are trying to just keep the ball away from 2 in a small area, and we had them learn a policy using reinforcement learning by just lots of experience. We'd run it overnight, come back, and the keepers were much better at keeping the ball away from the takers. And then we tried to transfer that to bigger scenarios, to 4 versus 3 or 5 versus 3 or 5 versus 4 or different areas, and explored different ways of taking the learned value function that I described and making it be relevant to the new scenario, even though it's different states and actions, different numbers of agents, and showed that we are able to do that, to have what we call, we could see jumpstart. So it would basically learn, have immediately out of the box better than random performance, and then also eventually get to higher level of performance in the long run by first being trained on the simpler problems and then having it transfer. We've also looked at scenarios, similar scenarios of what we call half field offense, where three robots go in, 3 agents go in trying to score on a goalie and a defender, and again change the number of agents doing this and showing that that transfer learning can work in this kind of scenario. So I mean, I can't go into the details in the time we have of how we made that transfer work, but we did, and we used it as a test bed and actually found multiple different ways of taking what's learned in the simpler problem and making it generalize and apply to these more complex problems.
Fantastic. Well, thank you so much for spending the time with us today. It's been a great webinar. I'm going to go ahead and close out, and sorry if I didn't get to your questions. We will record this session and send you the link to the YouTube video so that afterwards, if you want to go back and watch it, you certainly can. Wanted to thank our groups that brought this together, and that is our Texas Engineering Executive Education. We have some upcoming courses you might be interested in. We launched recently graduate certificates, and this is a new type of credential to UT Austin, where maybe you don't need an entire master's degree and you just need a shorter graduate certificate. So the Mechanical Engineering Controls certificate applications are still open for the spring semester, as well as the new Petroleum Engineering Data Analytics. And for those of you that are moving towards a professional engineering degree, we've got our Fundamentals of Engineering exam refresher course coming up soon. So check out our website for those. PTEX, the Petroleum Extension, has been adding some new courses to their list of live online courses, since we're adapting like everyone else. And you can see there we've got some LNG basics of liquefied natural gas, some meter assessment, a new one related to pipeline risk, and then material loss and measurement courses. So please check out the PTEX website for those oil and gas related courses. None of this would have been possible without the support from our groups, Texas Engineering Executive Education, the Petroleum Extension Service, PTEX, as well as our Office of Research Relations here at the Cockrell School of Engineering. If you have some lifelong learning inquiries or want to connect with the Cockrell School of Engineering about research, please take advantage of these websites and these contacts to reach out to us. Our next text talk is going to be Dr. David Mitlin on the topics of battery and corrosion. We'll send you a follow-up. So if you're interested in the next text talk, it'll be on November 6th at 10 a.m. And with that, thank you for joining us, and hook 'em.